Hello class, this is Adam Ward and I want to work through an exercise using Manning's equation. This is an example problem in which we've got a straight stream with a fall of 3 meters across a 1,000 meter long parcel of land, a discharge of 10 cubic meters per second given a bottom width of 4 meters, and the question is to find the cross-sectional area and velocity of this stream. Not given in the problem statement, but necessary is a value for Manning's n. We'll assume 0.035 for purposes of this problem. Now, we're not told anything about the geometry of the channel, but we're going to assume a rectangular cross-section, so 4 meters wide and y meters tall. So we can set this problem up using Manning's equation as discussed in class. Discharge is equal to area times velocity, or area times the remainder of Manning's equation, so shown here. As a reminder, hydraulic radius, the capital R there, is the cross-sectional area divided by the wetted perimeter, or A over P. And so we can go ahead and plug in the values that were given. And if you solve this equation as is, you would get a depth of 1.69 meters. Cross-sectional area of the stream is that depth multiplied by the width of 4 meters, or 6.76 square meters. And velocity we can calculate from Q equals A times velocity, and I end up with a velocity of about 1.48 meters per second. Now in class we also discussed making what's called the wide channel assumption, and when we make the wide channel assumption we assume that the width is substantially greater than the depth of the river. And if you were to do that, that 2y on the bottom, what you're doing is assuming that that's equivalent to 0. So it's a negligible amount of friction generated by the sides of the stream. And if you do that, the 4 meters on top and bottom here cancel one another out, and the hydraulic radius becomes just y, the depth. And so using similar calculations, you can estimate a depth of 1.32 meters, a cross-sectional area of 5.28, and a stream velocity of 1.89 meters per second. These differences seem pretty substantial, and so in this case I'm not sure the wide channel assumption was a good decision to make. One extension of this problem would be to figure out at what width the wide channel assumption would be tolerable to you, maybe meaning less than a 10% difference in the estimated area or velocity. Excuse me. As a further extension of this problem, consider a case in which this was, let's say, a channelized stream, and we undergo a stream restoration project and we add some sinuosity to the stream channel. So now over that same parcel of land you end up with perhaps 3,000 meters of stream, or a sinuosity of 3. That would be an extremely sinuous stream. What that means is the 3 meters of fall is now spread out over 3,000 meters, or we end up with a change in slope. I wrote delta S on the slide for you. I'll let you work through the mathematics on your own. The solutions that I come up with are shown here if you do not make the wide channel assumption, and on the right hand side making the wide channel assumption, slightly different values. So that's an opportunity for you to practice doing these calculations on your own. Beyond this, folks have asked me about providing some additional opportunities for practice. So some obvious extensions to this problem. You could resolve the problem if this was a 1-on-4 side slope for a trapezoidal channel. So a bottom width of 4 meters but a 1-on-4 slopes. You could think about setting this problem up and asking what would be the required bottom width and or the required Manning's n to limit the depth to perhaps 1 meter or less in the stream channel. And so the idea here being we want to specify a design to meet a desired depth of flow, preventing overbank flooding. Or you could address this problem thinking if you were given a velocity and a bottom width, could you find the depth of flow, the area of flow, and the discharge? And so those would all be alternative ways that you might apply Manning's equation to other problems in this class or that you may come across in your career. So hopefully this problem helps you see how to use Manning's equation, the impact of the wide channel assumption, and gives you some ideas about ways you can practice with Manning's equation on your own. Thanks, everyone.